My name is Joe Weiss, and I've been asked to speak about control system cybersecurity and essentially what that means to things like water and wastewater. And I wanted to thank the American Association of Water Distribution and Management for allowing me to do this. What you're going to hear and see is the perspectives of cybersecurity from the engineering side of the world. So the first thing I wanted to talk about is, why do we even care about cybersecurity? As a control system engineer, my primary focus is reliability, availability, productivity, and safety. Nowhere did you see the word confidentiality or privacy. What I'm worried about is I want to keep water flowing. I want water to continue to meet EPA requirements. And I want the systems to do what they're supposed to do in as optimal a manner as possible. And if electronic communications can in any way affect that, then I worry. If it cannot, then it's just not that important to me. This to me is a really important slide because it really explains why there are so few people, effectively almost in the world, who really understand what is going on with trying to secure, I don't want to even use the word critical infrastructure, but securing infrastructure. What you see is the big world of IT, because that's where computer science lands. And you'll see 4 arrows because most people in cybersecurity are coming from IT. You see control system engineering with 1 arrow. Part of that is because the control system world views security is an impediment to doing what needs to be done. And we've got to change that mindset that it isn't hurting us, but we need to do it because it's going to help. And the dot is the dot of people who understand enough about security and how systems operate to be able to adequately understand how to secure these systems. And I've heard numbers used that there's maybe on the order of 500 or so people that fit in that dot. And that's not for water, that's for all. What you're looking at here is how a control system for any industry would look. When you're toward the right side, what you're looking at there is what most people view as a control system, which is, if you will, the Windows operator displays and what would be in a control center. Pretty much all of that is what you would expect to see in an IT environment. Prior to this thing called Stuxnet, that's where security ended. Because of Stuxnet, these funny things called programmable logic controllers are now being looked at to try to make sure that they can't be compromised. And one of the big issues there was that logic or firmware could be changed, and they could be changed by somebody who wasn't supposed to change it, whether it was maliciously or unintentionally. And again, the communications that you see on the bottom, if you will, are predominantly Internet Protocol communications, or Ethernet, or your standard IP network stacking. Then you get all the way to the left where you see things like control valves, motor controls, sensors, things like that. Those are the things most people wouldn't know if they tripped over them. But that's where I call you go boom in the night. And it turns out in this convoluted fashion, where you have security, you don't go boom in the night. Where you have no security is where you can go boom in the night. And what's more, the networks that would be used where you're talking about these sensors and control valves and motor controls, etc., those networks have no security in them. And what's more, it is really, really difficult, possibly not even possible, double negative, to incorporate things like crypto in those types of networks. So we're sitting here trying to figure out how best do we secure the unsecurable. And one of the things I'm showing in this box, and I'll get to in a minute, is the unintended consequence of what these networks did. Because what you've got over on the far left is what is really happening at the actual process. In other words, where you have a boiler or where you have a, where you're actually trying to work with the water process itself. And what you measure is analog. That's the actual world. And somehow it's got to get converted into a digital signal and from there to Ethernet. That's where you see these serial to Ethernet converters. Part of what I'm talking about could be viewed in a funny sense as IoT, Internet of Things, though I have a major problem with the word Internet. But it's at that converter that you start to see real issues that start to come in with security and safety. Now, what I wanted to talk about is that this is real. There is most of the incidents that occur that are considered cyber incidents may not be malicious. In fact, this is one of the things I want to define because it really gets lost. In the IT world, a cyber incident is effectively defined as you're connected to the internet, you're using a Windows interface, and somebody has compromised your data. But the NIST and presidential, I believe it's Policy Directive 41 definition of a cyber incident is simply electronic communication between systems that affects either confidentiality, integrity, or availability. Nowhere is the word malicious used. The most important letter to my part of the world isn't even in there, and that's the letter S for safety. Because what we're most concerned about is equipment can be damaged or people could be harmed. I have a database I've collected over time, and by the way, it's not public, but I've been able to identify well over 1,000 control system cyber incidents to date. And by the way, more than 50 of them have been in water and wastewater. The impacts have ranged from significant discharges to significant equipment damage, major electric outages, and there's been more than 1,000 deaths to date directly from control system cyber incidents, and well over $60 billion in direct impacts. We have very few control system specific cybersecurity technologies. We don't have very much control system cybersecurity training, and we don't have much control system cybersecurity policies. One of the other things that's missing is we do have cybersecurity policies, business continuity policies, physical security policies, but many of the times what you have in there can actually go against what you need to do to secure a control system. And one of the things DHS and others who are heavily into this world will tell you, you should never be connecting a control system directly to the internet. And yet, there have been studies that have identified there are more than 2 million control system devices directly connected to the internet and counting. And many of these are gateways. And this is how black energy got into our electric grids all the way back in October 2014. And it's also, in a sense, how the attackers got into the Ukrainian grids. Our systems weren't designed to be secure. I think that's given by most. So what needs to be there, and I think you heard it earlier, resilience and recovery have got to be addressed. What you're looking at, too, in these pictures, starting from the upper left, this is complete destruction of a turbine. The next one was the Aurora vulnerability, where you essentially destroyed a large generator. And the same thing can destroy any AC induction motor. At the top right was the DC Metro train crash that killed, I forget if it was 11 or so. Middle left was the San Bruno natural gas pipeline rupture in the Bay Area. Middle was the Olympic pipeline rupture in Bellingham, Washington. The middle right is very important. That was the Marucci wastewater sewage discharge case. And the reason I want to talk about that was a malicious attack by an insider who never worked for the utility, but he was the one who installed that SCADA system. And what he did, because he didn't get the job he was promised, he remotely opened the sewage discharge valves, ultimately dumping more than 1 million liters of sewage onto the grounds of a Hyatt Regency. The first 20 times he did it, they thought it had to have been a mechanical or electrical problem with the sewage discharge valves. They finally caught him the 46th time he did it on a traffic stop. So when you're asking, is it real? Absolutely. That's 2000. Have things changed? Not nearly enough. Bottom left was tilting an offshore oil platform. Middle was the complete destruction of I believe that was a 6,400 megawatt hydro station that killed 75. This last one on the right was a brand new Navy ship that control system software ended up essentially damaging the transmission system, and that brand new ship had to be towed in the final 40 miles into Norfolk. What you're looking at is this crosses all industries, and it certainly affects water and wastewater. The other case I wanted to bring up that I think is important, this was not malicious that we know of, but remember, we have no forensics when you start talking at the control system layer. Not the control network, but control system. And that was, we had a water system that ended up pumping water from a Superfund site, a well that was a Superfund site, directly into the drinking water system. This actually occurred, and the alarms were not operated. That's basically how it was found. But just to give people an idea, this is real. And it doesn't necessarily have to be malicious to cause major problems. What is it that we're really worried about? In the IT world, it's just the network. In our world, it's a cyber-physical system. We're most worried about the physical system. In the IT world, you hear this term, advanced persistent threats, that something is in there for a long time. In our world, we have systems that were designed from day one to effectively be vulnerable. That's not how we viewed it, but that's why I call this persistent design vulnerabilities. In the IT world, you want to be able to get access to data. If you want to cause real damage, the level 0, 1, and 2 come from a term called the Purdue reference model. And level 0 is the actual process. So it's like the electric grid itself. If you want to cause damage, you want to cause damage at the process. What I'm working on now is the fact that none of our sensors have any security in them. So how can you secure anything if you can't trust your measurement? The last part is what's called level 2, which is what happened with Stuxnet. That's where you compromised the logic that goes into the controller. What you'll notice here, all of these, number one, can cause actual damage to equipment or harm to people. And essentially all of these are in a sense below where the normal, if you will, IT network monitoring would occur. This is the unintentional, one of the unintentional consequences of the networks. What we had in the past as engineers is we would look at and figure out, are the sensors working properly? Is the system working properly? And the way we would find that would be the wiggles in what's called the process noise. And you would see it at the sensors. So you would know if the vibration was increasing, you would know if a sensing line is clogging, you would know if you will, things are starting to go south. But the unintended consequence were those gateways that I showed you earlier have filtered out all of this noise, which makes it pretty much impossible for a network monitoring system to know what is actually going on at the process. And we've got to get back to know what is happening. One thing I should mention is I gave a presentation on this at the DEF CON cybersecurity conference in July of last year. And it was all about the fact we have no security in these sensors, and how we would know has essentially been removed. About 3 or 4 months later, right before I was getting ready to give a keynote, I noticed I had a like on my LinkedIn account. And it was on this DEF CON presentation that we have no security in these sensors. And when I clicked on the face to find out who it was from, if you believe Google, it was from a senior engineer from a water company in Iran. And what made it so interesting was this was publicly acknowledging that Iran is aware of these shortcomings. The holy grail of where we want to get to, and I say this as a control system engineer, for safety, security, productivity, regulatory compliance, etc., is to be able to know what's happening at the actual process and then cross-correlate that to what the networks are telling us. Because that then says, if there's a vulnerability on a network, for the first time we would be able to say, do we care? Or conversely, by having this monitoring, we could know, is somebody actually trying to compromise the process? These are the issues I'm hoping people get a better feel for. What I'm hoping most of all is we can get senior management, whether it's in the water industry, whether it's with the vendors, whether it's government, but to get senior management to take cybersecurity of these systems as seriously as they take cybersecurity of the IT networks. And with that, I wanted to thank the American Association of Water Distribution and Management for allowing me to talk about this subject. Thank you.